Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future, binge watching us right before the exam. So today I'm going to finish this first part about the introduction, and then we'll go over the relational model, which is actual math, but don't worry, I'm going to try not to scare you too much. So let me just finish. I had a few slides left from the introduction. So what you need to understand in terms of terminology, because this is something that many people confuse, what a database is and what the database management system is. The database is the data itself. PostgreSQL is not a database. IBM is not a database. The data is the database. The products like PostgreSQL and so on, these are database management systems. This is software that manages and stores the data. And this together is called the database system. And a system, like many other systems, like an ecosystem and so on, right? There's plenty of other kinds of systems, computer systems. So this is a database system, the database, so the data, plus the database management system. All right, and then the architecture, I'm not going to worry you too much about the internal architecture of a database management system, even though we'll have a week towards the end of the semester in which I'll do this a little bit. But basically, it's all about metadata and data, right? So the metadata is about the columns you can have in the tables, the schema, and so on. I'll come back to that. And the data is what you actually have in the table. And so you have all kinds of features in there. DDL is data definition language. That's to change the schema and the structure of the tables. And the ML is data manipulation language. This is to change the data that there is in the table or to query the data. Transaction managers are something we are going to look at in a few weeks. It's basically to deal with the case that 1,000 people access the database at the same time, which is one of the really useful feature of a system like that. Imagine you're a bank, you have millions of customers, so you want to make sure that everything runs smoothly. All right, and then of course, eventually everything is stored on disk, but thanks to a database management system, this is something you don't need to worry about anymore because it does it for you. Just a few words on schemas. So this is the DDL part. Of course, we'll cover them a bit in the relational model as well. But basically, the schema of a table is kind of what the data looks like from far away, right? So it's the structure of your tables, what you have in your columns. For example, the birth date must be a date. And some integrity constraints. For example, if you have some tax return that has some register ID, it should point to an actual person living in Switzerland in the database, right? So this is the kind of integrity constraints you can get from a database management system. Right, and just to give you an idea, this is what it can look like when you have the structure with the columns of your table. Then you can specify for every column the types that you can have here. So these are additional constraints. Plus, you can have some constraint that the quantity must be positive, and so on and so on. And the database management system will prevent you from doing mistakes. If you try to put a negative number in there or to do something that wouldn't actually fulfill the constraints that you have here, then it will complain, right? That's the benefit. Seems like Polybox wants to update. Just do it later. All right. That's an example, since we are in Switzerland, of some financial stuff. So let's say you have customer IDs, security IDs, and quantities. So this is an example of the sort of data you can have. And then you can relate the data at the bottom with the schema at the top. And you notice that what you have on the left, which is data you could have in the table, fulfills this. So this is an integer, this is a string, this is a positive integer. But here you see you have something here in customer ID that is not an integer. And you have here something in quantity that is negative, right? So this would be invalid. And in fact, PostgreSQL or any database management system would reject this, would not even let you do it, but this it would accept. Right, so it puts a lot of safety nets in there that prevents you from doing things you don't want. Then what typically happens between the metadata and the data is that the metadata, so the structure of the table, the schema, and so on, you set it up once. We'll see how next week concretely with SQL, and then you let the data evolve. So once you have set up your table, hopefully your customers will connect to your websites, they will place orders, they will register, create accounts, and so on. And so the tables, they evolve. When a new customer registers, it's going to add a record for the customer. When they place an order, it's going to add a row to the customer, to the order table, and so on and so on. There is a name for that, a fancy name, it's called a universe, a table universe. It's basically all the possible tables that you could have that fulfill your constraints. Okay, and we'll see, and that again is now probably in 3 or 4 weeks with actually SQL. You will need to understand, and I'm here for that, that there is a difference between the languages where you tell the computer what to do versus the languages where you just ask for what you want. And the difference I like to give is the same as between cooking at home, where you open a recipe book and it tells you to do this and that with the ingredients. That's an imperative language, so you actually have to do it yourself, as described in the recipe book. A declarative language would be like going to the Polymensa and asking for the veggie menu. That's declarative, right? And they cook it for you. It's all taken care of. In a way, that's a form of data independence. Maybe we could call it food independence if we want, but that's basically the same idea, right? You basically outsource. And then you don't have to worry anymore about the details. So this is it. And in fact, it doesn't mean that there are no imperative languages in a database management system. It's just that it's only the people who implement the database management system who write in C++ and Java. So the people who develop PostgreSQL, they probably use a language like C++, Java, a language like this that is imperative. But you as their user, you use a declarative and functional query language like SQL, right? And the database management system takes care of interpreting and translating everything you write in SQL. They translate it to C++ and Java and make sure that it runs as fast as possible, optimizing things on the way, and so on.
Sorry, the question?
Yes.
Concerning the integrity constraint slide. So the question is, what if I want to enter -87 items since I own a number of clients products that have not yet arrived?
So you want to limit the number of rows to 7, something?
Maybe it means in the future you might want negative numbers, but you cannot really anticipate how to deal with that.
This is true. So this actually is an important point that especially startups typically experience. It is true that when you define a schema like this, you have to be very careful because you plan for the long term. You can change it, of course, later on. That's okay, but it's not easy. It's something that you shouldn't do very lightly, especially not in production. At least not in production without thoroughly testing. So if you want the option to leave the schema open or to not put constraints just now, then there are technologies for this that's called NoSQL. This is in big data for engineers, right? So in this course, we will assume that there is a schema and there are constraints that you must ensure. You can change them later, even though it has a bit of a cost. And there are technologies taught in big data for engineers that allow you to free yourself from the constraints, right? But of course, there is always it's always a compromise to make, right? If you have that, you lose other things. So that's the idea. Did I answer your question? Yes, wonderful. Thank you. Yes, so this is what I was telling you, that it's all a matter of layers. So you have C++ and Java. You don't need to worry about that because it's the engineers of PostgreSQL that deal with this, that implement the database management system. And you as the user can use SQL or even UIs on top of that, user interfaces. And actually, if you want to go even more to the physical layer, what happens with C++ and Java is that they get translated to something called assembly code or bytecode, which is a language even closer to the CPU, the CPU, the processor of the computer that the computer can understand. So this is what computer scientists call a computer architecture or an architecture when you do these sort of things. All right, so data independence, we have a declarative language on the logical layer and an imperative language on the physical layer. And it's possible to even change the physical layer, like the PostgreSQL team, they release a new version every year. Now I think it's version 16. And every year in the course, we just upgrade to the newer version. It was probably 15 last year, but it doesn't change what I'm teaching you. It's still the same language SQL. So it's just going to get faster and there are going to be things more optimized, but that's the benefit of data independence. You can swap the physical execution. It automatically translates to what's called the plan. That basically is the recipe, and then it implements it. And in big data for engineers, we will even see that we can also swap this for 1,000 computers or even more in a data center, and it still doesn't change the logical model. You can still use SQL for your queries. Yes, the question over there? We can try. Yes? The imperative language, that's the implementation of the physical layer. That would be basically the code that is written in order for PostgreSQL to work. You have in fact the same thing for Excel, for or LibreOffice, or all of these software. They're all implemented in languages like this, and this is all what computer scientists call the physical layer. Now I just have to maybe say a word of warning: is that this notion of logical layer, physical layer, it is not absolute. It is not absolute, because you might have people who implement things on top of SQL. Some fancy, imagine that they implement, I don't know, a voice assistant like ChatGPT that can issue SQL queries. From the perspective of the people who do this, who use ChatGPT to connect, SQL would be a physical layer then, right? The database would be a physical layer, and the logical layer would be the large language model, right? ChatGPT. So everything is basically a matter of perspective, right? It's really a multi-layer architecture. And when you say logical and physical, it's always that you are somewhere in the architecture drawing a line. Everything that's above is logical, everything that's below is physical, right? That's the idea. And for the purpose of data independence, this is where we draw the line between imperative and declarative. These are how the layers are. So this is the data independence for computing stuff, right? Writing code. And you also have data independence for the actual data. Then the physical layer would be the disk, the zeros and ones that are stored on the disk, the files and directories. And the logical layer would be the tables themselves, right? So data independence is both for computing stuff like here and for the actual data. All right? Did I answer your question? Okay. And this is the last slide of the introduction. And now we are going to start diving into the actual material, serious stuff. Do we have any questions so far? On Zoom? Nothing? All right. That was only the introduction, right? So I just waved my hands and talked with very general things. But now things are going to get more interesting with the parts 2. All right.